So let me just remember one fact that I want to write down, because it will also lead us to like a famous quantum slogan or principle that I feel obligated to tell you about. Even though this slogan or principle of quantum, some people are really excited about it. It's this no cloning principle, and they're like, this is the most fundamental aspect of quantum mechanics. And I actually think it's like not at all important, or it's like trivial, but I'll let you be the judge. Okay, so to get to that discussion, we have to remember first this thing, that for this basic distinguishing two states problem, as long as the angle is not plus or minus 90 degrees, there's no perfect algorithm. Okay, the only place in this graph where the failure probability goes to 0 is at plus or minus 90 degrees. Okay, so for example, any algorithm for, ket 0 versus ket plus, these are two things at, let's say, 45 degrees, with one-sided error, this requirement that you have to have one-sided error, has error at least 1/4. Wait, a half. Make a note. Yeah, that's what we argued before, that like, you cannot beat this simple algorithm that we saw last time. On the other hand, we did see last time that in like an alternate scenario where you can get multiple copies of the test vector, so if you're allowed to get, let's say, m copies of test, and here this is really like all m of them are ket 0 or all m of them are ket plus, you just don't know which is which, you're trying to tell the difference, then you can reduce your failure probability or false negative probability or whatever to 1/4 to the power of m. You just run, you do this test that has failure rate 1/4. I keep saying a quarter, so my notes are wrong. You just keep doing this test that has failure rate a half, like m times, and it's like a no means no or yes means yes algorithm. So whenever you get the output yes, you're just done. You're like, I'm sure it's yes. And if the only way that you can get a false negative, if it's like all m times, you see the answer no, even though the true answer is yes. So the probability of that happening in like m repetitions is like half to the power of m. And that's actually good. I mean, this failure rate goes down to 0 exponentially the more copies you have. Okay, so like one copy, you're in big trouble. Your error is a half. Many copies, you're actually in good shape. You can make the distinguishing error probability as small as you like. So we could call this fact star maybe the no distinguishing principle. This is not like a real term that people say in quantum, but I'll say it. Okay, for non-perpendicular states. Just says for this game, you have two states, they're not at 90 degrees, and you're trying to distinguish them. There's no perfect algorithm that 100% of the time distinguishes them. And what I want to claim is that this implies this more famous principle that somehow caught on as a popular concept called the no cloning principle. And what does the no cloning principle say? It says there's no physical device or mechanism or quantum algorithm with the following property, that it takes as input one copy of a state of a mystery state, we'll call it test, and then like pumps out many copies of this same state. So it pumps out like a stream of particles all in state test. Okay, so that's the no cloning principle. It says like, there's no like algorithm that if you put into it like a mystery, let's say qubit state, it analyzes it, blah, 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 and then like it can effectively give you a copy of like a new qubit subroutine where this new qubit subroutine like makes qubits in the state test. Like the principle says like that's impossible. So like it can't be cloned, this input state. And let me remark that this might seem like a strong requirement that you got to be able to like, take in the state, somehow analyze it, and like pump out like arbitrarily many copies of the same state. But it's like equivalent to say that like you can't even make, one more copy. Or you can't even have an algorithm that takes in like one qubit in some mystery state test, and like it sort of outputs, has the ability to output like 2 qubits each in the state test. And that kind of follows immediately, because if you could like turn 1 into 2, then you could like save 1 and to take the other one and do the operation again and turn the second one into 2, and now you have 3. You save 2 of them, and you use the third one on the supposed device again, and now you have 4, and so forth, and you could make as many as you want. So, yeah, sometimes people think of it this way, just like there's no algorithm that takes in 1 copy of test and kind of spits out 2 copies of test. But I want to claim that like this arrow, this no distinguishing principle is more fundamental than the no cloning principle, because as I'll show you in 1 second, this fact easily implies that fact. So since we saw this fact, now you also know this no cloning fact. So as I erase, you can think about why that might be true. But I'll prove it now. So I'm going to prove that arrow, and the proof will be by contrapositive. I'll prove that, like, if you could clone, then you could distinguish. Okay. So suppose there were some algorithm or physical mechanism to clone. Okay. Now I'm going to show you how you'll solve the, let's say, distinguishing problem for, ket 0 and ket plus with error better than a half, but just with 1 copy. So then, given, just 1 copy of a qubit in state test, promised to be either 0 or plus, we could, in contradiction to no distinguishing, distinguish with 1-sided error better than a half. In fact, much less than a half. How? Well, just do the cloner and make like 1 million copies of ket test. And then it's like you're in this situation. And you can get, exponentially small failure probability. That's it. Just, clone, test, many times, m times, and then, use smiley face, where smiley face is this observation. So that's it. And in fact, this, if you think about it, this shows an even stronger principle than no cloning. So we're like, oh, you can't make 1 zillion copies. In fact, you can't even make just 1 more copy. In fact, you can't even build a cloner whose only job is to work when the mystery state is either 0 or plus. So can't even succeed in cloning. It promised that the mystery state is 0 or plus. Okay, or any 2 non-perpendicular states. On the other hand, it is possible to have a cloning device if the cloning device only has to work for, like, say, ket 0 and ket 1. Because how does a cloning device work? It takes in the mystery state, which is either ket 0 or ket 1. It measures it. It finds out perfectly 100% whether it's 0 or 1. And if it's 0, then it's like, great, I'll just pump out a bunch of new qubits. And if it's 1, then it's like, great, I'll just pump out a bunch of new qubits and toggle each of them. OK, any questions about this? Yeah. Yeah, they're almost equivalent to each other, actually. So on the homework, you'll prove this a bit more formally. Here, I basically tried to argue in words, saying, like, what are you going to do? Like, you can rotate them, but they're still at 45 degrees. There's nothing else you can do. And that's basically correct, but you have to dot a few I's and cross a few T's. And no cloning, once we know, there's no distinguishing. Once we know that there's, like, no cloning. There's also, I'll get to you in a sec. There's also kind of like a reverse, like, what if I alternately forgot about all this and somebody just directly proved no cloning principle to you, which you can do. It's also, like, quite easy to prove directly, the no cloning principle. What could you infer from that about these, like, learning a mystery state problems? You can convince yourself that the no cloning principle, like, itself implies what you might call, like, a no learning principle. And what does no learning principle mean? It means there's no algorithm that, given a mystery qubit state, can, like, do some stuff to it and exactly figure out the amplitudes. Or even, like, get the amplitudes to arbitrary precision. That statement that, like, given one copy of a state, learning the amplitudes is impossible, that's what you might call a no learning principle. It's also true because, conversely, in fact, these are equivalent. So on one hand, suppose you could clone. Then you could take one state and make, like, a trillion copies of it. And it's not hard to see. We'll do this later in the course. But if you have, like, trillion copies of an unknown state, then just by measuring it, like, a bunch of times at a bunch of different angles, you can pretty much eventually figure out its angle. So you could learn to arbitrary accuracy. And on the other hand, like, if you could take one copy of the state and learn its, amplitudes or learn its angle perfectly, then you'd be great. Like, if you learned, I learned it, it's at 30 degrees, so now I can clone, because I can just, like, pump out 1,000,000 qubits and rotate them all by 30 degrees. So it's pretty easy to see. I mean, I said it in words, but, like, no cloning is equivalent to no learning. But this one's, like, even stronger, like, a little bit stronger, because it, like, implies all of them. Question? Yeah, you would be able to get error, like, maybe half to the m if you had m copies. But what you would be able to do if you could make a trillion copies would be to beat success probability at half with one copy. And this is saying, like, if you only get one copy, you cannot beat success probability at half. Another reason that, like, I don't get, like, in my life overly excited about the no cloning principle is it's not inherently a quantum thing. It has nothing to do with, like, amplitudes per se or I don't know, unitaries, because you should always remember if somebody says to you, like, oh, you get one copy of a quantum state, one copy of a qubit, it's very, very similar and analogous to somebody saying, here's a coin that comes up heads with some mystery probability p, and you're only allowed to flip it one time, okay? Like a one-time flippable coin or like a sticky coin, you, like, flip it, you can see if it's heads or tails, but you can't reflip it. Like a sticky coin is, like, extremely similar to, like, a quantum state. The quantum state also has a problem. You can measure it and get some information, but, like, you can't, like, keep remeasuring it. And there's also, like, a no cloning principle and a no learning principle or no distinguishing principle for, like, sticky coins. Like, imagine, I don't know, like, you're interested in, like, the learning problem. So I give you, like, one sticky coin, and I'm like, it comes up heads with some mystery probability. Maybe it's 20%, maybe it's 80%, maybe it's 30%. Try to figure it out. 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 Try to f it's pretty obvious that you're like, well, if I can only flip it one time, I'll see heads or tails. What am I going to do? I'm not going to be able to learn whether it's 20% or 30% or 80% if I can only flip it one time. And yeah, that's true, and that's like a no learning principle for, sticky classical coins. You can't even tell the difference between like a 90% heads coin and a 10% heads coin with one flip. You get like a reasonable idea, but you can't perfectly tell the difference. The only, sticky coins that you can distinguish are like a 100% heads coin versus a 0% heads coin. If you know it's one of those two, then indeed, with one flip, you can solve it. So all I'm saying is it's true that like, classical probability and quantum states are not the same thing, but sort of the idea underlying this no cloning principle or no distinguishing principle is just like a feature of the fact that like you can only get like one time information out of the object. It's not like truly like a quantum thing.